Before we begin with combined loading, we first need to understand what type of quantity stress is. Stress is a fundamental concept in engineering that describes how forces act on a material. However, stress is not just a simple quantity or magnitude, nor a vector. It is a tensor, a mathematical object that carries both magnitude and direction. For more information on stress, watch the video of the efficient engineer made on stress before watching this video. The stress tensor contains 9 components, 3 normal stress components and 6 shear components. Firstly, we have sigma xx, the stress, acting on the x-axis, sigma yy, the stress, acting on the y-axis, sigma zz, the stress, acting on the z-axis. We also have 6 shear components, tau xy, tau xz, tau yx, tau yz, tau zx, and tau zy. Now that it's understood, let's begin with combined loading. Combined loading refers to a situation where a structural component or a material experiences multiple types of loading simultaneously. These loadings can include axial load, shear load, torsion, or bending forces. If you need more information on each type of load individually, make sure to check out the channel of the Efficient Engineer. Now let's take an example on combined loading with the dimensions shown. A 13 mm diameter bolt hook is subjected to 600 newtons, and we need to determine the stress component on the volume element A located on the shank. We first need to find the components of the force on the x and y axis. Now, we cannot use the components directly since they are not acting on the neutral axis, so we need to move them. The 519.6 newtons in the x direction creates a moment on the neutral axis equal to its magnitude multiplied by its distance from the neutral axis, meaning it will be equal to 20.784 newtons meter. Now, we just move the forces to the neutral axis, since we created the moment created by the forces. Now, to find the reactions at A, it's going to be a simple equilibrium process, equal to 20.784 plus 300 multiplied by 50 multiplied by 10 to the power of minus 3, equaling 35.784 newtons meter. After that's done, we now need to extract a volume element A from the shank and find the forces acting on it. Forces acting on the volume element will be sigma xx only. This is because the volume element is located directly at the top of the shank, meaning there will be no shear forces exerted on it, where sigma xx equals moment multiplied by y over I, which is the area moment of inertia, plus the force over area, which denotes the axial load. We just substitute everything in its place, and we get 169.8 megapascals. To visualize this answer, we have to take another look at the question, but from another angle. This time, we're going to have to take a bigger look at the whole cross-section. At first glance, the first question that might pop into your head would be, why are the forces acting on the neutral axis not zero? This is because this is the combined loading. And to understand it more in depth, we need to separate each type of stress acting on the cross-section individually. Here, we have 2 types of loading. We have the bending moment stress and the axial loading stress, where the bending moment stress conveniently has the forces on the neutral axis equal to 0. And when we sum up the bending stress plus the axial load, we get the combined loading.